So when it comes to vertical motion in terms of analyzing things with forces, these are your three unique situations. In terms of the vector diagram or free body diagram, which is what is very important for everything we're doing here for the next few days, you need to understand that although the force due to gravity acting in each of these three cases is the same, I'm assuming it's the same object, okay? Even though the force of gravity is the same, if it's accelerating up, the applied force upwards is greater. If it's accelerating down, the applied force upwards is less. And if it's not accelerating at all, then the applied force upward is exactly equal in magnitude to the force of gravity. So if we label all of these, this is the force due to gravity. This is an applied force. This is the force due to gravity. This is the applied force. Again, force due to gravity and applied force. How is this useful in terms of analyzing the motion? Well, in this case, the net force has a magnitude that's equal to the magnitude of the applied force minus the magnitude of the force due to gravity. You can build a formula from that. It would be, if I go one step further, it would be ma equals the applied force minus mg. And as I like to say, the physics is done here. If you're doing a problem where this applies and you've gotten to this point, the physics is done. You just then have to put numbers in, right? I mean, I suppose that's part of physics. If the acceleration is down, looking at this free body diagram, how would you find the net force's magnitude? You would take the magnitude of the force of gravity minus the magnitude of the applied force. So this would become ma equals mg minus F applied. How many of you, and I include myself in this group, found yourself doing math in school, maybe in junior high, maybe even in high school, and you do some work and you get a negative answer and you know it should be positive and you realize you subtracted the wrong way? It doesn't work that way here. If you subtract the wrong way, you will not get the negative of the answer. You will get a wrong answer, okay? You need to know the order in which to subtract those. And of course, we had an extensive discussion yesterday about this. I mean, what are we going to do here if the acceleration is 0? I think the quickest thing to do is just to say that the applied force is equal in magnitude to the force due to gravity. I don't think it's useful necessarily to write F net equals F applied minus Fg when F net is 0. I think it's better to just cut to the chase and say that mg must be equal in magnitude to the applied force. And that's what this really boils down to. Now, today things are going to be different because we're going to be dealing with accelerated motion on an inclined plane. So it's not up and down. It's something totally different. But that kind of encapsulates or summarizes everything you need to know about vertical motion and Newton's second law. So take a look at your work, please, 1 to 5, I think it was. Does anybody have any questions? Go ahead, Nate. Number 5. Okay, so let's take a look at number 5. Okay. We have an 8 kilogram object that's pulled vertically upward by a rope. The tension in the rope is a constant 95 newtons. So something I didn't mention, I tried to stick with yesterday this concept of applied force, but I could very easily do the following. And I'm going to point this out because when I got to university, I was thoroughly confused by this. My prof did this. And she was talking about those being forces, and I'm wondering, well, why aren't you using F for force? Very often an applied force is a force that's due to tension in a cable or a rope. So if I'm pulling upwards with a force of 95 newtons, the tension in that rope will be 95 newtons. So I'm mentioning this as well, not just so that you're not confused if you see it later on, but in university, I might actually do that. I have to stop myself. Sometimes I just want to write T for tension. Sometimes as well, what we can write, sometimes you see that, F sub T, which just means a force because of tension. But it's an applied force. So now let's get back to question 5. So we have an 8 kilogram object pulled vertically upward by a rope. What is the velocity of the object after 1.1 seconds? Ultimately, everybody, at the heart of this is a kinematics question. The object was initially at rest, so VI is 0. It's moving for 1.1 seconds. You're asked to find VF. From a kinematic standpoint, everybody, knowing 2 things is not enough to find a third. You need 3 things to find a fourth. And what's happening here is dynamics, which is related to forces, is being connected to kinematics, which is related to motion. We can determine the magnitude of the acceleration using a force analysis. And once we know that acceleration, we can solve the problem kinematically speaking. So this would be where many of you might look at this and go, okay, yeah, I get it. You have to wade your way through this logic, and then you start doing the following. It's wrong. Why is it wrong? Well, because it's not force equals ma, it's net force. You have to do an analysis, and whatever you put in for net force has to be the sum of all of the forces. So don't fall into that trap of getting complacent, just laid back and going, oh, F equals ma. We are dealing here with a situation, maybe what we should do first of all is determine whether the object will accelerate up or down. And I know it's going to accelerate up, not because of the fact that the force is upward, but because I know that force is more than the weight of the object. Right? So just as an exploratory kind of calculation here, what is the force due to gravity? It's mg. I don't think I need to write down 8 times 9.81. We could figure out what that is, though. 8 times 9.81 is the force due to gravity. So 78.48 newtons. Didn't space this out very well. Let me move this down. What that means is we have 78.48 newtons down, Nate, and 95 up. So the 95 up, 95 is more than 78. We now know that to answer number 5, we are looking at this situation on the left. So F net equals the applied force upward, its magnitude, minus the force due to gravity's magnitude. I hope you'll forgive me if I don't say magnitude each time. I get tired of saying it. I want to just say F net equals F applied minus FG. So I hope you understand if I do say that, I'm just saying the magnitudes because I didn't put vector symbols. So we put the MA in here. This is the applied force. This is mg. Well, actually, I don't think we even need to put mg anymore because we've calculated it, right? But we can put in the 8 kilograms. Remember, we're after the acceleration. Then the 95 newtons minus the 78.48. So if I subtract those two forces, I get the net force. Then I divide by the mass to get the acceleration. I think it's 2.19. Did I subtract wrong? 16.52? Thank you. Is that better? Okay. So the acceleration is 2.065. Meters per second squared. We can pop that over here into our kinematics list of 2.065 meters per second squared. Now, I mean, I don't want to just hand wave this away as if, well, now you can finish the question. It's been a while since we've done some kinematics. You know, we haven't really been focused on it. So you're looking for a formula here that does not have D. And the only formula that does not have D is acceleration equals change in velocity over change in time. So we have A equals VF minus VI over T. I don't think it's necessary to worry about vectors here. I was very careful when I taught kinematics to say we always use vectors, but now that we've gotten more accustomed to things, I believe I've mentioned this to you, but I'll mention it again. The negatives in the kinematics equations only ever become important if you have objects which can change direction, or if you have objects that are slowing down. So an object thrown upwards, you have to use negatives where they apply. But an object moving upwards with a constant acceleration, we don't need to worry about it. So now we can solve the problem. We take that acceleration of 2.065 meters per second squared. This is equal to VF, which we want to find, over the time of 1.1 seconds. Nate, why did I not put VI here? Right. So we cross multiply and you get to 2.3 or whatever it is. Yeah, 2.3. Does that do it for you? Any other questions? Okay. Close your books and take out a sheet of paper. All right, I'll have those marked and back to you tomorrow. So again, the objective is to solve problems involving various applications of Newton's second law. When I first learned physics, it's almost always the case, particularly in post-secondary, when you study this. And if you go on to post-secondary, you'll study in physics much of the same stuff we studied here, but it's just at a higher level. Basically, you are told, here's Newton's second law, solve any of these problems. I've tried to break it down into different types of questions. So today what we're looking at is inclined plane examples. Remember, when you're applying Newton's second law of motion, you have to follow these steps. I suspect that on this quiz, many of you don't need a free body diagram. But that's only because that's all we've been working on for a day. You know, when I get to pulleys, or inclined planes, or inclined planes with pulleys, that free body diagram is very important. So the free body diagram is drawn, and it shows you all of the forces acting on the mass. And the reason that's important is you have to know what to do to those forces to get the net force, because it's the net force that determines the acceleration. So you use the free body diagram to find out what you do with all of the individual forces to get the net force. You build an equation setting the result equal to ma and solving the problem. So to begin with, what is the acceleration of the mass on this incline if there's no friction? I've got your formulas given to you on the right for inclined planes, the parallel and perpendicular components. This is not a difficult question when you see it. but you have to draw the free body diagram. The free body diagram will contain a force of gravity that is parallel to the ramp, a force of gravity that is perpendicular to the ramp, and it will also contain a normal force. So this force is the force due to gravity that is perpendicular to the ramp. This is the force due to gravity that is parallel to the ramp. And this is, whoops, drew that in the wrong place. This is the force of gravity that is parallel to the ramp. And what's that third force up top called? The normal force, right? And that's it. Those are the only forces. And notice that I put vector symbols above the forces because the directions are important. So if I want to find the acceleration, see, here's something I don't think I mentioned to you. Let's try to get this into our heads. From here on in, unless you're dealing with a kinematics problem, acceleration is found by looking at forces. Specifically, the net force will equal the mass times the acceleration. And I've dropped the vector symbols here because all I'm telling you is the magnitude of the net force gives you the mass times the magnitude of the acceleration. So you have to look at this diagram and say, what's the net force? And in this question, F net is FG parallel. I'm going to write something out here that I don't think you would ever write out, or you don't need to write out. But how do I know that? Well, I know that net force equals all of the forces added together. So the normal force plus the force of gravity perpendicular to the plane plus the force of gravity parallel to the plane. That's what net force means. It means I add the forces. And again, I'm trying to prepare many of you for post-secondary, which is going to be a few years away for some of you, but you still might have these memories of, oh yeah, I remember we did that in Way's Physics 20 class. It's important. I have vector symbols above what I just wrote, which is telling you that you add these forces including the directions, right? They're vectors. Okay. What is the sum of those two forces? It's 0. Because they're equal but opposite. So what we're left with is that the net force is equal to nothing plus the force due to gravity parallel to the ramp. Well, that's what I've put up here. Right? That's the conclusion that I came to, and I came to that conclusion by looking at the diagram. When I add all those forces together, all I'm left with is FG parallel. Now you have a couple of options here. You could certainly calculate FG parallel on the side and then set it equal to MA. I am a person who likes to do this. I'll build the equation here. MA, which is the net force, equals FG parallel, which is the force due to gravity, times the times the sine of the angle. So I don't know that you need to write what I'm going to write. I'm just in teaching mode right now. This is F net. This is FG parallel. But since they're equal, I just put them equal to each other. If F net is MA and FG parallel is FG sine theta, then I put them equal to each other. I can go a little further and write MA equals mg times sine of theta and I can solve the problem. The mass, which is 16 kilograms, times the acceleration equals the 16 kilograms times 9.81 times sine of 30 degrees. And what I will be finding is the acceleration along the parallel component orientation down the ramp. Do me a favor, take a minute and calculate that. See if you get 4.905. You're going to have to take 16 times 9.81 times sine of 30 degrees and then divide that by 16, and you get 4.9 meters per second squared. Before we go on, I would like you to take a look at all of your work. You can look up here. I'll resize things so that we can see everything on one page. So on the left-hand side is just us reasoning out what the equation is going to be that's going to lead us to the answer. And on the right-hand side is all of our work with that equation. What would we have gotten for an answer if the mass was 76 kilograms? And there's two groups here. There's a group who grabbed their calculator and started multiplying and dividing, and then the lights kind of went on. And there's another group that said, well, you know what? It's going to be the same. And it's going to be the same because we didn't even need to put that 16 kilograms in. At this point in time, right here, I could have divided both sides of the equation by the mass and got that. So sometimes when you build an equation, something cancels, in this case mass. And for that reason, listen very carefully, you would be expected to solve problems like the following. Find the acceleration of a mass that's on a 30-degree incline when there's no friction. Because when you do it properly, you end up developing this equation that's in the bottom right-hand corner of your screen where we can cancel the m's. And I know what happens is we get to the exam, and a hand goes up sheepishly, and I go over, I say, what's the problem? I think you're missing the mass in this question. No, I'm not missing the mass. You're missing the fact that we don't need to know the mass in this question. Okay, so be aware of that. Let's try another one. Find the acceleration of the mass in the previous question if the coefficient of friction is 0.23. So this time, there is a force of friction. Well, that means we have to sketch this again. And I don't want you just putting a new diagram on top of the old one. We need to sketch this. I didn't give you rulers today, so I will freehand along with you. Here's our ramp. Here is our mass that's on the ramp. What are the forces acting on that? Well, there is a force of gravity that is parallel to the ramp. There is a force of gravity that is perpendicular to the ramp. I mentioned this yesterday. I want to mention it again. If the angle of the ramp is quite low, the perpendicular component will be more. I mean, think of an object. Think of an object on this table right now. there's a force of gravity acting down on it, right? If I lift it to an angle of 5 degrees, do you agree most of gravity is still acting perpendicular? Okay. At what angle would these two components be equal? 45. So if the angle is less than 45, your perpendicular component is greater than the parallel component, which I didn't put. If it's, let me repeat that. If the angle is less than 45, the perpendicular component is greater. If it's more than 45, the perpendicular component is less. And if it's at 45, they're equal. What other forces do we have? Well, we also have this normal force, which I can't think of a situation where it wouldn't balance the perpendicular component. It's always going to do that. But then we have a force of friction. And we have the same problem that we encountered yesterday. I set it up yesterday so we would kind of be prepared for this. I don't know how long I should draw the force of friction. So this is a case where I believe it will be beneficial for us to calculate this force of gravity parallel and calculate the force of friction. Okay? And I'll explain why in this case we shouldn't just set up the whole equation in a minute. But let's calculate the force of gravity parallel. Well, that's equal to the force of gravity times the sine of the angle. Didn't we find this already? We found this in the previous question, didn't we? Because it was the exact same scenario. It was, well, actually, I guess we never really did calculate it, did we? Some of you might have. So let's calculate it here. I'm going to take the mass. Alex, was it 16 kilograms? 16? So 16 multiplied by 9.81 multiplied by sine of 30 degrees. Make sure you are in degrees, right? I did the calculation kind of in my head last time, so I didn't check. And you get 78.48. I guess we did calculate that somewhere, didn't we? Oh, yeah, it's right up there. So 78.48 newtons. This is, look, I don't believe for many of you this is a difficult problem, but it's got so many moving parts, figuratively speaking, that it can be confusing. So what else do I need to find here? Listen, I guess I need to find all of the forces because I need to find the net force. Do I need to actually calculate Fg perpendicular? Well, no, because I know it's going to cancel with Fn. But I also want to know the force of friction. The force of friction is mu. The force of friction is mu times the normal force. And we can dispense with the vectors here. What's the normal force? The perpendicular component of gravity. This is what I mean by lots of moving parts. This is going to be mu times the component of gravity that's perpendicular, because these two forces are equal but opposite. And I can go to that box at the top of the page there that tells me the perpendicular component is the force of gravity times the cosine of the angle. So this becomes force of friction equals mu mg cosine theta. So I can calculate that. Mu was 0.23. Mass is 16 kilograms times 9.81 times cosine of 30 degrees. And I will know how many newtons the force of friction is. $31.26. Give a few of you a couple minutes to catch up. Is that what you're getting for the force of friction? Okay. So at this point in time, before I write anything down, I'm saying that's 31.26 newtons, which is less than the force of gravity that's acting towards the bottom of the ramp. So when I draw this, this is my force of friction. Maybe I could draw it a little bit longer. The force of friction has a magnitude of 31.26 newtons. So will the box slide? Yeah, there's more force down the ramp than there is opposing. But now we get to the same thing you did on the quiz. You looked at the two forces and you said, this is almost always going to be the case, everybody. In the end, you'll have two forces that are opposite. Not always, but most of the time. So the net force will always be the bigger minus the smaller. Of course, without directions. Right, look at the diagram. You got 78 newtons down the ramp. You got 31 newtons opposing it. So now we can put MA equals FG parallel minus force of friction. So we can put in the 16 kilograms times the acceleration equals the 78.48 minus the 31.26. Subtract them and divide by the mass. Very similar to one of the quiz questions where you had to subtract the upward force minus the force of gravity and divide by the mass if you wanted to find the acceleration. .95. Okay. Just before we finish off this lesson and give you some time to practice a few on your own, did I need to give you the mass in this question? And I admit that I'm pushing the envelope here. Are we getting 2.95? Okay. I admit that I'm pushing the envelope. But you did not need the mass in this question because you have F net equals Fg parallel minus the force of friction. Well, F net is Ma. Fg parallel is mg sine theta. The force of friction is mu times the perpendicular component, which is mg cos theta. Oh. Divide both sides of the equation by mass. You do not need to know the mass. One final question. What would the acceleration of the mass in the previous question be if the coefficient of friction was 0.63? How many of you suspect you know the answer to this question? Maybe. I mean, why would I ask you another question if it was identical to number 2? I've increased the coefficient of friction, and I don't know. I think I've increased it enough so it won't slide. But this goes to what we did here. Before we committed to writing any equation, we wanted to look at the values of these two forces. We need to know which one's bigger, because that's how we set up the equation. Well, we already know the force of gravity that's parallel to the ramp, that's acting down the ramp, is 78.48 newtons, and it's in this direction, right? Along the ramp. The force of friction is mu Fn, which again, on an inclined plane, Fn is the component of gravity perpendicular to the ramp. So the force of friction is mu m mg cosine theta. Well, let's calculate mu mg cosine theta. Let's find the force of friction. This is going to be mu 0.63 this time, times the 16 times the 9.81 multiplied by cos of theta. Give me around 95, 96 newtons. No? I mean, it's going to be in the 90s, isn't it? 85? Anybody else? 85? Okay, my estimation was off. Wonder why. Okay. So about 85 newtons. Can you give me a 1 decimal place after that? 85.6 newtons. So the force of friction is, sorry, I asked and I didn't even register. 85.6? Yeah. Okay. 85.6 newtons. And that is a direction, in the opposite direction to that 78. So you want to be careful here, right? If I said, what's the net force? And you said, well, Mr. Way told us you take the bigger force minus the smaller force. You have to use a certain level of common sense here. The net force here is 0, right? Look, if I have a car that's in neutral and I'm trying to push it forward, I have to overcome the force of friction, right? If I push it with a force of 10 newtons and the force of friction is 20,000 newtons, does that mean as soon as I start pushing it, it moves backwards against me because the force of friction is in the opposite direction? No. Nothing happens until the force of friction meets or exceeds this force. Or rather, let me rephrase that. Nothing happens until the force that's trying to move the object meets or exceeds the force of friction. So if the force of friction is more, the net force is 0, which means the acceleration is 0, which means it doesn't slide. And that's it. I gave you 3 situations. They can be more involved. I could tell you in this question here, I'll go to a diagram. I could tell you that the coefficient of friction is 0.63. This would be a cruel question. What force is needed to move the box up the ramp? And what you would have to do is recognize that you have 78.48 newtons down the ramp because of gravity. You also have 85.6 newtons down the ramp because it's friction. We're trying to move it up so the friction's backwards. That means if I want to move it, I have to apply a force equal to the sum of those two to get it to move. Or I could tell you, you apply a force of 200 newtons. What's the acceleration? And it can be more than just 2 forces. Or I could tell you you're applying a force downwards. What's the acceleration? You have to be adaptable here. Anyway, you have a few questions that I would like you to do for tomorrow. I will get your quizzes marked and back to you by tomorrow. And tomorrow we have one more thing we want to look at, which is pulleys. And then next week we put it all together, potentially with pulleys and inclined planes. So get to work on those problems, please.